that for any x in H, if you take the trajectory of the solution of, say, your nonlinear evolution equation that with initial condition from x, S of t operated onto x, and you substitute this into v. Okay? You substitute this into v. Now this function can be treated as a function of time and a function of x. So this function as a function of time is non-increasing in t. Okay, so the v operated onto S of t x is increasing in t. In other words, v operated onto u, where the u is the solution of your nonlinear evolution equation, is non-increasing function in time t. So the first thing. The second thing, that v is bounded from below actually. Bounded from below. That is, you can find a constant c such that v of x is bigger than or equal to c for all x in H actually, okay? So, you're going to call such functions as Lyapunov functions. What are Lyapunov functions? They are continuous functions which are non-increasing in time and bounded below. Okay, so if you have such kind of a function, you're going to call this function as a Lyapunov function. And here's a basic property of the Lyapunov function. Here's a basic property of the Lyapunov function. So if v is Lyapunov, if v is Lyapunov, that satisfies definition, then v of x is constant. It does not changes for all x in omega limit set actually. So all x in the omega limit set, say, of u naught r, maybe. So v of x, say v of say y is constant for all y in omega limit set of x. Okay? So it's constant for all. So in other words, if you pick, so v is Lyapunov, and if you pick an element from stationary solution from corresponding to say initial condition x, then v should not change throughout the set actually. So v must be constant. Proof why this would be the case. Now, what we know about v of S of t operated onto x, okay, obviously x is from H, should write in this manner that for x in H, v of S of t x is non-increasing. Okay, is non-increasing. All right. So if it is non-increasing and bounded below as well, by definition, and v is bounded below, and actually you can also say that v of S of tx is bounded below as well. So v is bounded below for all x, so it should be bounded below for v of S of tx. Then you can treat this v of S of tx as a sequence in time actually. Okay, so I can treat this as a sequence in time. Now we know, and from your, say for example, first real analysis course, first of all, V of S of Tx is a real number, so this is a real sequence. So if I take T, I replace T by some sequence, okay, then we know, or maybe if we recall what we call so-called monotone convergence theorem, which says that if you have a sequence of real numbers that is increasing but it's bounded above, then it must converge. It converges to what? It converges to the supremum of the sequence actually. Okay? And if your sequence is decreasing, non-increasing, and bounded below, so it must converge actually. Okay? It must converge. Converges to what? It must converge to the infimum of the sequence actually. So V of T is non-increasing, otherwise it's decreasing, and bounded below. Okay? So as T goes to infinity, V of f of T x must exist actually. It exists. Okay? It exists. Okay? And this would be equal to what? The infimum of V of S of Tx for all t bigger than or equal to 0. And let's give this fixed limit a name, say V infinity. Now the V infinity is a fixed constant, which is, as I said, by monotone convergence theorem, it's an infimum of V of f of Tx for all t bigger than or equal to 0. Okay? And it's a fixed constant. Now I would like to show that if you pick an element y from, say, omega limit set x, your v must be constant and it should be equal to the value v of s. Okay? So now let's take say for example psi from omega of x. So by definition, there exists a sequence Tn that goes to infinity as n goes to infinity, such that S of Tn operated onto, say, S of Tn operated onto x converges to what we call psi. Okay? As n goes to infinity, it converges to psi. Yes, it converges to psi. And if it converges to psi, then by continuity, since V is continuous, the V of S of Tn operated onto x converges to V of psi. Okay? As Tn goes to infinity. In other words, that if you take limit Tn goes to infinity of the V of S of Tn x, this should converge to V of psi actually. Okay? It's equal to this. But this guy, we know from here, is equal to V infinity. Hence, we're going to say that no matter what psi you take from the omega limit set, the good thing about the Lyapunov function is that when it operates onto an element of element of omega limit sets, it gives you a fixed constant. So this is a constant, and this is true for all psi. This is true for all psi. So we define Lyapunov function. So what is the Lyapunov function on a complete metric space? If you have a continuous non-increasing and a bounded below function, it's Lyapunov. And we proved an immediate property of the Lyapunov function, that if you take the Lyapunov functional function or functional whatever, then it must be constant on the entire omega limit set. With this definition, now we are in position to define what you call the gradient system. Gradient system. Gradient system. What's a gradient system? A gradient system is a triplet in which H is a metric space, S of t is a C0 semigroup, and V is a Lyapunov functional. So this triplet is called a gradient system if following two conditions are satisfied. Okay? If following two conditions are satisfied. Number one, for any x in H, okay, you can always find an instant t0 such that the union of the trajectories s of t, say operated onto x, where t is bigger than or equal to t0, is relatively compact. Okay, so the first thing is that these orbits are relatively compact for any x H. In other words, no matter what x you take, for every x you can find an instant such that if you consider the orbits, okay, after the instant t0, these orbits, okay, are basically relatively compact actually. Okay, and you have to keep one thing in head. You can immediately see from here that if you know for your flow that your flow is a gradient flow, then this condition is satisfied. And if this condition is satisfied, then the last lemma that we proved about omega limit set, it requires this condition actually. So the assumption of that lemma would be true. And if the assumption of that lemma would be true, your omega limit set is already going to be compact and connected and, you know, what do you call, invariant actually. Okay, and hence is going to be non-empty. In other words, that there must be some stationary points to which the solution converges actually. Okay, so that's the beautiful thing about the gradient system, that the assumption of that lemma about the omega limit set, the last lemma about the omega limit set, are going to be satisfied. So this is the first condition that you get out of this condition. And here is another beautiful thing that you're going to get out of a gradient flow, is that if for t positive, s of t operated onto v of s of t operated onto x is equal to v of x, if this condition is satisfied. So if for any t, the v of s of t operated onto x is equal to v of x, if this condition is satisfied, then this x is basically a fixed point of the semigroup. Okay? Then this point x is a fixed point of semigroup. Then x must be, x is a fixed point of semigroup. X is a fixed point of semigroup. And in the terms of the PDEs, or the nonlinear evolution equation, if this is true, then x is not only a fixed point of semigroup, but it is actually and a stationary solution, a time-independent solution to your nonlinear evolution equation actually. Okay, we'll see that why. Okay, we'll see that why in one case. You can already see that, okay, if the S of t operated onto x is x, then you can, this S of t is basically the trajectory of the solution. And you are saying that the trajectory of the solution for all times is equal to what you call x. And hence you're gonna say, so its time derivate must be 0. And since u satisfies your evolution equation, so the x would also satisfy your evolution equation. But the time derivate would be 0. And hence you can say that x is going to satisfy the stationary version of your problem. Okay? And it could be a potential point. I'll write a lemma which will say that such a stationary points are the fixed point of the semigroups, are the points to which the solutions of nonlinear evolution equation will converge in long run. So if you want to find what are the functions to which the solution of the nonlinear evolution equation will converge in long run, just try to find the fixed point of the semigroups. Because these fixed points are not only going to be the stationary points, in other words, the solutions to the stationary solutions, but they are also going to be the points to which the solution of nonlinear evolution equation converges in long run. And why this will be the case? Because we will see that these x will be the elements of the omega limit set, okay, which does the job. Anyway, I'm speaking too much, but I'm trying to give you in an excitement that what a beautiful result this is. And this definition is that a triplet, a complete metric space S of t, V, you're going to call it a gradient system if for any x in H, you are always going to find an instant t naught such that such orbits are relatively compact. And if you have some t for which the v of s of tx is equal to v of x, then x is the fixed point of what do you call semigroup. And if this system is a gradient system, then this u of t, which is basically s of t u naught or x, for t bigger than or equal to 0, we're going to call such a solution of your nonlinear evolution equation is called a gradient flow actually. A gradient flow. So how can you know that a given nonlinear evolution equation is a gradient flow or not? Take its solution, okay, prove that its solution exists and it's unique, and prove that its solution and hence its semigroup corresponding to it satisfies these two conditions actually. Once it satisfies these two conditions, your flow or your solution can be treated as a gradient flow actually. And one thing that I would like to tell is that there are several kind of formulations of the gradient flow actually. Okay? So you will find different papers. For example, you see the Rothschild papers, you will find a different description of different but equivalent description of the gradient flows actually. Okay? Now, okay, imagine you have a nonlinear evolution equation that is a gradient flow. So what's so special about gradient flow? The answer is this theorem actually, theorem at the Gorolki. Now suppose you have this gradient system, then this condition is satisfied for sure. And if this condition is satisfied, you're going to say then for any x in H, omega limit set of that x. In other words, for any given initial condition, if you want to interpret it from the perspective of evolution equations, for any given initial condition, its omega limit set is non-empty. Okay, it's non-empty, it's compact, it's invariant, and connected. I don't need to prove it, because if H is a nonlinear evolution, is a gradient system, then for every x, this set is relatively compact. And once you have such a set which is relatively compact, there is an instant for which, after that instant, such sets are relatively compact, then you have this non-emptiness, invariance, and connectedness of what do you call your omega limit set actually. Finally, there is another interesting thing actually. So if you want to find this omega of x explicitly, moreover, omega of f, omega of x consists of fixed points of S of t. Okay? So if your flow is a gradient flow, then you want to find what you call omega of x. Just don't do anything. Try to find the fixed point of S of t. Those fixed point of the semigroup are going to be the elements in omega of x. Okay, this is what the interesting fact that you have about the gradient flow. So determining omega limit set completely reduces down to what do you call finding the fixed point of the semigroups. Okay, fixed points of the semigroup. This is what. And what are the fixed point of the semigroup? The fixed point of the semigroups are basically the stationary solutions of your given nonlinear evolution equation. Just solve stationary solutions of your nonlinear evolution equation. Those will be the fixed point of your semigroup and the elements in omega limit set. Okay? So I don't need to prove this first part. I'll just show this last part actually, that why elements of omega of x are the fixed points of the semigroup actually. It's not difficult to show, just a one-liner. So let's take, say, psi from say omega of x. Okay? And I want to show that this psi is a fixed point of omega limit set. Okay? Now, after introducing the Lyapunov function, we proved a lemma about the Lyapunov function, that Lyapunov function is constant on every single element of the omega limit set. We proved that V of psi is constant. Okay, it's constant, and it's not only constant, but it's equal to V of S of t operated onto psi. Okay, for all t bigger than or equal to 0. So V on every single element of the omega limit set is constant, and not only constant, but this is also true. So we showed it. And once you have it, combine it with the second part of the gradient system actually. So if your H of St is a gradient system and this holds, then such a points are the fixed points of the semigroup. So this shows that by 2 of the definition of the gradient system, of the gradient system implies that psi is a fixed point of semigroup. Okay, psi is a fixed point of semigroup. Okay. What is next thing? The next thing is, so this completes the proof. Next thing is a simple corollary to this result. Okay, and that corollary is also interesting, and that says that suppose your HS of PV is a gradient system, okay, then suppose ST is gradient system, and suppose, let me write it explicitly, HS of PV is gradient system, and set of fixed points of S of T semigroup, okay, of semigroup is discrete actually. So it's a discrete set, maybe finite, maybe infinite, but a countable discrete set actually. So you have a gradient system and the set of, and you know that the set of fixed point is a discrete set. In other words, set of stationary solutions. So there are some finite or countable number of stationary solutions of your given nonlinear evolution equation, if you want to interpret them in the terms of nonlinear evolution equation. Then for any x in H, you have this miracle. And what is that miracle? That S of Tx converges to an equilibrium point. S of Tx converges to an equilibrium point. In other words, stationary solution actually. It converges to an equilibrium point. In other words, you know the long-term behavior of your evolution equation, that it converges to some equilibrium. Okay? So it's not exploding in long run, it's not just wandering around in long run, it just goes to equilibrium. If you know two things, if your flow is a gradient flow, and your system is gradient system, and your set of fixed points of the semigroup is discrete, then your trajectories of your solutions, starting from some initial condition, are always going to converge to some equilibrium point in long run. And that equilibrium point, as I'm saying again and again, are going to be the fixed point of semigroups, are the stationary solutions of your nonlinear evolution equation actually. Okay? Stationary solution of your nonlinear evolution equation. Alright, so this is it. So these are the two basic results that we need. Now let's do one example actually. So the equation that we are considering, that I proposed in the beginning, I'm going to show that it's a gradient flow actually, or its solution is a gradient flow. Okay, it constitutes a gradient system. Okay, a gradient system. Then you have to try this for your equations actually. And since it constitutes the gradient system, so you have the results which tells you that there are points to which the solution will converge in long run. So the solution of your evolution equation are going to converge to a stationary solution actually in long run. Okay. So let me recall our equation. What was the equation that we had in the beginning? So we had this equation. ut equal to Laplace u plus u minus u cube. U onto the gamma is 0.